They resonate throughout the natural world in beautiful mathematical proportions. Like mystical building blocks, they combine to create the music that we love. In the ancient words of Pythagoras, there is geometry in the humming of the strings. There is music in the spacing of the spheres.
Hello, my name is Dr. Kurt Sander, and this is Music Theory Simplified. When we begin the study of music theory, we don't start off on some sort of quest to understand the human artistic mind. That would be a difficult thing to do. Rather, we begin the study of theory with something more mathematical, more scientific. We begin with the study of intervals. An interval is simply what you get when two notes sound together. About 2,500 years ago, the ancient Greeks were fascinated with musical intervals. They believed there was something special about the relationship between two vibrating pitches that could help them explain the natural world more clearly. Now, you don't have to be Greek or a scientist to know that there are certain intervals that sound good or pleasing to our ears, intervals that we call consonant. And there are intervals that sound dissonant or harsh to our ears.
What causes this? Science says it's not personal taste.
Rather, it has something to do with the relationship between two pitches.
When two musical notes are played together, their frequencies combine to create a relationship that we call an interval ratio.
What's interesting is those intervals that sound pleasing to our ears have interval ratios that are very simple, whereas those intervals that sound harsh or dissonant have much more complicated interval ratios.
But let's simplify this. In an interval ratio of 3:2, all this means is that in the time it takes the top note to vibrate 3 times, the bottom note vibrates twice. This is a very simple ratio, and it sounds very consonant to our ears. But let's use a real-life example to make things even more simple. Let's say you were relaxing on a beautiful summer day in a hammock, and as you were lying there, you heard a bee fly overhead. Now, if you had perfect pitch, you could identify that that bee was buzzing on an E flat. Science tells us that that E flat vibrates at 156 times a second, so that bee is flapping its wings at 156 times per second. That's a pretty big bee. But let's say a moment later, you were still lying there, and you heard another bee go by. And having perfect pitch, you could identify this as an E flat as well, but this one an octave higher than the previous E flat. An octave is simply a type of interval where both notes share the same pitch name but are separated by 12 keys on the piano. But to a scientist, an octave is an interval where the higher note vibrates twice as fast as the lower note, creating a 2-to-1 interval ratio. So here's where it gets fascinating. If we knew that big bee flapped its wings at 156 times a second because it's an E flat, we know that an octave above that, or the little bee, flaps its wings twice as fast, or 312 times a second. That's more along the lines of a normal bee.
The study of intervals and their corresponding ratios is a fascinating area of inquiry, but it really goes beyond the scope of what we're trying to do here. What I want to do here is get you up and running, identifying intervals when you come across them in music.
Interval size.
The first step in identifying intervals is determining an interval size. This is a very easy process, and if you can count, you can figure out the size of an interval. So the process simply involves counting the lines and spaces between the notes on a musical staff. The one important thing you need to remember, however, is that the bottom note always begins with the number 1. Let's start with an easy one. Here's an interval that's very small. We're going to start by counting with the bottom note, number 1, and then move to the next line or space. The next note is on a line, so it's a second. Let's try another one. Start with 1, count lines and spaces. This is also a second. Let's try one that's a little bit larger. Again, we begin by counting 1, and then we count lines and spaces going all the way up. The line above this note is 2. The space above that line is 3. The line above that space is 4. And finally, that third space is 5. So this interval is the interval of a fifth.
So is that all there is to it? Just counting?
If counting was all there was to it, you wouldn't need music theory simplified. So let's look at the other aspect of intervals. We've already talked about size, but now let's talk about quality, which is the other aspect. Size is how something appears on the musical staff, but quality involves how many half steps, or piano keys, separate the two notes. When we refer to musical intervals, we have to refer to both size and quality, and this is where it gets just a bit tricky. It's really important not to confuse these two distinct parts of the interval. For example, this first interval will always be a fourth, while the second will always be a fifth, even though they look the same on the piano keyboard. Also, the same size interval can reveal a different number of half steps, depending on an interval's quality. Here we have two intervals of the fourth. They're both fourths because of how they appear on the musical staff, but they're different qualities because one has more half steps than the other, based on the piano keyboard.
Confused yet? Well, if you are, don't worry. Let's talk about interval quality, and I think that'll clear things up.
Interval quality.
As we mentioned before, an interval's quality is determined by the half steps that separate the two notes. So once you determine an interval's size, you must then calculate the number of half steps that separate them. So let's say that by counting lines and spaces, you determine that you have an interval the size of a fifth. Well, unless you know the number of half steps that separate those two notes, you don't know what kind of fifth it is. Not all fifths are equal. I suspect part of the problem is that we have these things floating around our musical scores. We call them accidentals, sharps and flats, and they raise or lower pitches. The problem is really in how we've been conditioned to think about them. Because a sharp raises a pitch, it does not necessarily mean that it makes an interval larger. The same for the flat. Just because it lowers a pitch doesn't mean it makes an interval smaller. Let me give you an example. This is the Ivanov family. They're moving into a new house with their 3 children, and that house has a roof and a floor. For the sake of visualization, let's pretend that the roof was the top note of an interval, and the floor was a bottom note. If the Ivanov family wanted to make more headroom in their home, they have the choice of either raising the roof, or adding a sharp to the note, or they can actually lower the floor, or add a flat to the lower note. So in both cases, the sharp and the flat serve to make an interval larger. But let's say they wanted to save on their heating costs and to reduce the headroom in their home. They could do the opposite. They could raise the floor, or add a sharp on the lower note, or they could lower the ceiling, or add a flat on the top note. So in this case, both the sharp and the flat can serve to make an interval smaller.
Not everyone struggles to identify distance between two notes as they appear on a page. But if you're one of those people for whom spatial reasoning is not particularly a strong point, this visual might come in handy.
Let's begin by figuring out how we describe an interval's quality. We use a lot of different terms when referring to an interval's quality. Terms like perfect, major, minor, diminished can be very confusing. How do we sort all this out? Well, let's begin by dividing interval qualities into two specific categories. There are two basic types of intervals. Those that are perfect, which include the octave, the unison, the fifth, and the fourth, and those that are imperfect, which include the third, the sixth, the second, and the seventh. How we label intervals in terms of quality depends on which category the interval resides in. Let's begin with the easiest interval of all, the octave. And we said the octave resides in the perfect category. A perfect octave is an interval where both notes share the same pitch name and have the same accidentals. On a piano keyboard, if you were to count up 12 semitones, you'd find that the letters start to repeat themselves. But there's really no need to count all those semitones. If you just look at the score and see a lower and upper note that share the same letter name, you know it's an octave. If the interval has no accidentals, that is sharps or flats, or if both notes have a sharp or both notes have a flat, we have a special name. We call it a perfect octave. But what if the accidentals were not the same? What if we had a sharp at the top note, making the interval 1/2 step larger? We call this an augmented interval. Any perfect interval made larger by a 1/2 step, we call augmented. And since no one writes words anymore, we can use this little handy-dandy plus sign to symbolize augmented. But what if the interval were smaller? If we add a flat to the top note, we've made the interval smaller. A 1/2 step smaller we call diminished. And since no one writes words anymore, we can use this handy-dandy little degree sign to indicate a diminished interval. Now let's see how good you are at this. Remember, if they share the same letter name, and they share the same accidental, or they both don't have accidentals, you know it's a perfect octave. So this first one, D to D, no accidentals, yes, it's perfect. The next one, F sharp to F natural, same note, different accidentals, not perfect. The third interval, E flat to E flat, sharing the same note, sharing the same accidental, yes, it's perfect. And finally, D flat to D natural, not the same accidental, even though it's the same pitch, it's not a perfect octave. So our goal here is really identifying perfect octaves. You probably will never come across an augmented or diminished octave, but you sure can impress friends when you do find one.
So you can see that identifying octaves is not that difficult. But it's important that we know this process because now we're going to look at the important interval of the fifth and how we can identify perfect fifths. If you wanted to waste a lot of time, you could sit down and you could study and memorize that a perfect fifth is exactly 7 semitones in size. But we don't have to do that. I've got a trick for you. Wherever you are, whether you're in a class or you're sitting at home or you're in a bus terminal somewhere, I want you to repeat this after me. And if you do this, you'll never get a perfect fifth wrong again.
So repeat after me. Space to space, line to line, accidentals match, perfect and fine. But watch for the B's. Let's repeat that. Space to space, line to line, accidentals match, perfect and fine, but watch out for the B's.
So what is this talk about lines and spaces and B's?
Well, it's a very simple rule. If it's a space to a space or a line to a line, we know that it's perfect without counting half steps. If we just see that the accidentals match, it will equal a perfect fifth, or 7 semitones in size, except when that bottom note is, yep, you guessed it, a B. You might be wondering, what makes this true? Well, let's take a look. If we have a perfect fifth, we know that it's 7 semitones wide. But within those 7 semitones, on the piano keyboard, you always find a place where there are 2 white notes touching each other. You can see them right here. If you look at our second interval, which is also a perfect fifth, it's also 7 semitones wide, and also you find a place with 2 white notes next to each other. Between this E flat and B flat, again, 7 semitones wide, and there's those 2 white notes again. But when you look at the lowest note, which is a B, and you look at how many places you find those 2 white notes touching each other, you find that there are 2 cases where white notes touch each other, and that makes it only 6 semitones wide, which means any time that you have a B as its lower note, you're going to have to do one of 2 things to make it perfect. You're either going to have to raise the ceiling by adding a sharp to the top note, and that makes it perfect, or you will have to lower the floor using a flat, making it also 7 semitones and a perfect fifth.
So if you memorize that one simple phrase, you will always be able to identify a perfect fifth. But it gets better than that. When identifying perfect fourths, we have a similar phrase.
So here we have 4 intervals of a fourth, each showing the same kind of space line or line space configuration. So repeat after me: line to space, space to line, accidentals match, perfect and fine, but watch out for flies. So just like the perfect fifth, the fourths work the same way, except a perfect fourth is 5 semitones. Between the upper and lower pitch, you always find a place where those 2 white notes are touching. There they are right there. And then between the notes D flat and G flat, you find the same sort of thing, these 2 white notes touching. But when the bottom note is F, there is no place between those 2 pitches where you find 2 white notes touching, which means that the interval is slightly larger than a perfect fourth. And what do we do to make it smaller? We either lower the ceiling or raise the floor with an accidental. So if you remember bees and flies, you will always, always, always get perfect fourths and fifths right without counting half steps.
So the key here is remembering bees are for fifths, flies are for fourths, and you'll never have to count another half step again. Just one other thing, if it's smaller than a perfect interval, whether it be a fourth, fifth, or octave, we're going to call it diminished. And if it's 1/2 step larger than a perfect interval, we're going to call it augmented. Well, it couldn't be any more simplified than that. Hopefully, you'll get a chance to practice these things. And just remember, you don't need to count half steps. You just need to remember bees and flies. Well, that's all the time we have for this video. This is Dr. Sander reminding you, as always, keep it simple.